Welcome to the second part of our series on galaxies. After focusing on our own galaxy in the last video, we now want to move outside the Milky Way and explore the other galaxies in the universe. Or at least some of them. After all, their total number is estimated at several trillion, and even in our immediate intergalactic surroundings there are still tens of thousands of galaxies. But first, let's take a look at how the exploration of galaxies over the last few centuries has led to our current view of these objects. More than 1,000 years ago, long before the invention of the telescope, the Persian astronomer Al-Sufi was probably the first to report on our neighboring galaxy, in the constellation of Andromeda, as a blurred patch of light. Once the telescope was invented, around 1600, countless other nebulous objects with a similar appearance were discovered, which had been invisible to the unaided eye until then. Especially during the 18th century, astronomers found hundreds of objects with the still primitive telescopes of the time. In 1755, the German philosopher Immanuel Kant proposed the theory that these objects could be distant Milky Ways like our own. He called them island universes. With this assumption, Kant was far ahead of his time, but this theory was still very controversial at the beginning of the 20th century. By no means all the blurry spots discovered in the night sky were galaxies. Nebulae, as well as open and globular star clusters, also appeared diffuse and unresolved with the telescopes of the time. Moreover, some observations were incorrect, as they are not reproducible today. In the late 18th century, in order to avoid confusion with comets, which also looked like hazy spots when observed with the telescopes used at the time, the French astronomers Charles Messier and Pierre Méchain compiled a list of more than 100 nebulae. This list is known today as the Messier Catalogue, and it contains not only nebulae, but also open and globular star clusters. The Andromeda Galaxy was given the number 31 in the Messier Catalogue. But Messier and his contemporaries could not reveal the true nature of this object. From the middle of the 18th century, thousands more nebulae were discovered in the night sky, in particular by William Herschel, who was born in Germany, but soon rose to become the most respected astronomer in England. He found many of these objects from 1782 onwards, using some of the largest telescopes of his time. The biggest one had an aperture of 1.2 meters or 48 inches. In the following century, the British nobleman William Parsons, the third Earl of Rosse, spent his considerable fortune on the building of even larger telescopes. He set up an observatory on his manor, Bear Castle in Ireland, for which he had the instruments made under his personal direction. This included the Leviathan, a huge telescope that was completed in 1845. With a primary mirror of 1.8 meters or 72 inches, it was the largest in the world at the time. The Earl of Rosse mainly used this telescope for observing the nebulae, and he was able to identify spiral structures in 14 of them, which was doubted for a long time. He saw spiral arms for the first time in 1845, just a few weeks after commissioning his Leviathan on M51, known as the Whirlpool Galaxy, but also on the Pinwheel Galaxy M101. As there was no photography at the time, these visual observations were sketched. In 1888, the Danish astronomer John Dreyer published a much more extensive compilation, the New General Catalogue of Nebulae and Clusters of Stars, NGC for short, which included many of the star clusters and nebulae discovered by William Herschel and later by his son John Herschel. When it was completed, the new catalogue listed 7,840 objects, including those from the older Messier catalogue. M31, the Andromeda Galaxy, for example, was recorded in the NGC as number 224. Two extensions to the NGC were published in 1908, the Index Catalogues, or IC for short, so in total, the NGC and both IC catalogues contain more than 13,000 objects. A decisive step towards determining the distances of galaxies was taken by the American astronomer Henrietta Swan Leavitt in 1912. Leavitt was one of many female scientists working on cataloging stars at Harvard University at the turn of the century. Women could be paid less than men and were generally considered detail-oriented and suited to the often boring work of data analysis. They were also not allowed to operate the telescopes, which limited their astronomical opportunities. Nonetheless, some of the most important discoveries in astrophysics can be traced back to the Harvard women. For example, Annie Jump Cannon and Antonia Mori made fundamental contributions to the spectral classification of stars. Henrietta Leavitt's special task was Cepheid stars. These variable stars change their brightness from day to day or week to week. She noticed that the brighter stars generally had longer periods. The brighter the star, the longer the cycle of its variability. With some of these stars in the Small Magellanic Cloud, a companion galaxy of our Milky Way, Leavitt discovered that the duration of their light variation period provides a measure of their luminosity, and this made it possible to determine the distance to these stars. A few years later, in 1917, the world's largest telescope since the Leviathan, the 100-inch Hooker reflector, designed by George Ellery Hale, was put into operation on Mount Wilson, in California. It was soon to be used for revolutionary discoveries in the field of astronomy. Thanks to the groundbreaking discoveries made primarily with this telescope, in 1920, a scientific debate arose about the true nature of spiral nebulae. The venue was the American Academy of Sciences in Washington. Harlow Shapley, a young astronomer with unconventional views, lectured on his work on globular clusters. In addition, he reported on his calculations of the Milky Way's diameter and on the position of our solar system within the galactic disk. Unfortunately, Shapley's calculations were incorrect, as they resulted in a size far too large for our galaxy. On the other side was Heber Curtis, an older and reputable astronomer. Curtis gave a lecture on his recent discoveries of novae, bright variable stars, in spiral nebulae, and proposed his conclusion that these nebulae must be located far outside the Milky Way. Shapley vigorously disagreed and countered with his own results, showing that the spiral nebulae must be quite close. He argued that the universe consists only of our Milky Way galaxy and that there are no other island universes. Ultimately, either of the two opponents was able to convince the other. This dispute, later known as the Great Debate, was only settled a few years later by Edwin Hubble, and in favor of Curtis. So, we have known just for about a century what these objects really are, namely distant Milky Ways. They are indeed island universes, just as Immanuel Kant had predicted nearly 2 centuries earlier. Edwin Hubble set to work in 1923 with the Hooker reflector. His aim was to capture images of the Andromeda Galaxy and several other neighboring galaxies. In these images, for the first time, the edges of the Andromeda Galaxy were resolved into individual stars, due to the capacity of the large telescope. This allowed Hubble to identify Cepheids among these stars, just as Henrietta Leavitt had done before. As a result, Hubble was able to determine the distance of M31 to be around 900,000 light-years. Although this was significantly less than the distance known today, as Hubble's method still had some errors, it was clear that the Andromeda Galaxy was far beyond our Milky Way. This finally disproved Shapley's theory. Later, together with Milton LaSalle Humason, Hubble discovered the connection between the redshift and the distances of galaxies. This observation was soon attributed to an expansion of the universe. A few years earlier, it had been detected that most galaxies exhibit a redshift in their spectra. Fainter and distant galaxies showed a higher redshift than closer and brighter ones. The redshift therefore appeared to increase with the galaxy's distance. Today, this is referred to as Hubble's law. At first, this effect was wrongly attributed to the Doppler effect. It was assumed that the galaxies were simply moving away from each other, and therefore also away from the observer. And the further away they were, according to this idea, the faster they moved. The Doppler effect occurs in any type of wave, including sound, as a change in frequency or wavelength, as soon as the observer and the source move relative to each other. When a car honks its horn, as it approaches us, we hear the sound waves at a higher frequency. If the car drives away from us, the opposite is the case. As the distance increases, the frequency becomes lower and its sound deeper. In case of electromagnetic waves, such as light, the change in wavelength is visible in the spectrum. A light source moving towards the observer causes the emitted light to become shorter wavelength. It shifts into the blue part of the spectrum. This is known as blue shift. If the light source moves away from us, the emitted light becomes longer wavelength and shifts into the red part of the spectrum. This is the red shift. The same effect occurs when the light source is at rest and the observer is moving towards or away from the source. In everyday life, of course, this is not as easy to recognize with light as with sound. However, it can be calculated that you must drive a car at a speed of at least 146 million kilometers per hour towards a red traffic light for it to appear green, due to the Doppler effect. Yet in an expanding universe, where the speed of light is not infinite, the correlations are somewhat trickier than on Earth. If the redshift was caused by the Doppler effect, very distant galaxies would have to move at insane speeds of 90% of the speed of light and more. This assumption was therefore fiercely contested from the outset. In fact, no galaxy, either today nor in the past, has ever moved at anything close to the speed of light. The redshift discovered by Hubble is not due to the Doppler effect and should therefore not be understood as the galaxies moving away from each other in space. It is space itself that is expanding, or rather space-time. The galaxies are, so to speak, floating with the expanding space-time. From these observations it was possible to deduce the so-called Hubble constant, which describes the linear relationship between the radial velocity and the distance of a galaxy. This proportionality acts as a mediator between the two quantities of speed and distance, in other words, how quickly the velocity of galaxies increases with their distance. But the name Hubble constant is misleading, since it is by no means constant. Its value has probably changed continuously over the billions of years. So, the cosmological redshift, as it is also known, is fundamentally different from the redshift caused by the Doppler effect. This is why the galaxies themselves do not become larger, nor do the stars and planetary systems and planets and everything on them become bigger in size. On smaller scales, gravity counteracts the expansion. And in the atomic and subatomic scale, it is the fundamental forces, such as the electromagnetic force, the weak and the strong interaction that prevent atoms and elementary particles from expanding. Reading books about astronomy, you often must deal with statements like this: the distance to this galaxy is 12 billion light-years. This means that the light from this galaxy has traveled 12 billion years to reach us. We are therefore looking into the distant past, into a time when our Earth did not even exist. But is that really the case? Is looking into the distance always a journey into the past too? Or to put it another way, is the distance of an object in every case a measure of the time span which light has taken to reach us? We all know that a light year is the distance covered by light in 1 year, at a speed of around 300,000 kilometers per second. And that's about 9.5 trillion kilometers. But is the light propagation time always identical to the distance? Or how far away is galaxy number 1 really from galaxy number 2? In fact, this is purely a question of definition and depends on how the concept of distance is interpreted. In everyday life, it's quite easy. In the simplest terms, distance is anything I can determine with a measuring tape between point 1 and point 2. For example, supposing we have 2 cars parked in a lot, you could simply measure the distance between car number 1 and car number 2. However, on the other hand, if both cars are moving, measuring the distance between them is complicated. Of course, because the distance between them is constantly changing, while they keep moving. And things are much more complicated in the intergalactic universe. We see light from a distant object, which was emitted long time ago and from a place where this object is no longer located. So, in this case, how exactly do you define the distance? Cosmologists therefore generally do not use light years or parsecs to indicate the distances to very distant galaxies. Instead, they use the value of redshift, or the z-value. Due to the expansion of the universe, A larger z-value means a greater distance from us. The larger the z-value, the further into the past we can see. However, this is not a distance in the conventional sense. As the universe is around 13.8 billion years old, we can only perceive objects whose light was emitted a maximum of 13.8 billion years ago. However, as space has expanded considerably since then, the places from which these objects once emitted their light are now much further away than 13.8 billion light years. Probably at least 3 times that distance. As confusing and surprising as this may sound, it is currently estimated that the radius of the observable universe is 46.5 billion light years. This boundary of the observable universe represents the range in which any information have found its way to us after the universe became transparent to visible light, radio waves, and other electromagnetic radiation. Anything beyond this horizon is too far away to be visible. Nevertheless, in the billions of years since the Big Bang, all the galaxies may have moved much further away from their original position. But how do we know how far away these objects really are? Over the course of time, various models and methods have been developed to determine distances in intergalactic space. However, for the reasons just mentioned, and many others, the further away the objects are, the less accurate the measuring methods and therefore the results. So-called primary methods are suitable for determining the distances of relatively close objects within the Milky Way or in nearby intergalactic space. They are quite accurate compared to the secondary and tertiary methods, which are used to achieve cosmological distances, but their results are sometimes highly scattered. However, even the primary methods do not allow us to determine exact distances. For example, astronomers can measure the distances within our local group with an accuracy of several tens of thousands of light years. The currently most accurate distance value of the Andromeda Galaxy, for example, is between 2.52 and 2.56 million light years. So, there is an inaccuracy of around 40,000 light years in this measure, which corresponds to almost half the diameter of our Milky Way. For even more distant galaxies, the uncertainties continue to grow, up to the order of millions of light years. I would just like to briefly introduce the 3 most important methods used today for galaxies. We have already learned about one of the most accurate methods. It is the relation between period and luminosity found in pulsating variable stars such as the Cepheids. The longer the pulsation period of these variable stars, the greater their absolute magnitude or luminosity. From the period, the average absolute brightness can be determined and thus the distance of the Cepheid. This means that these variable stars become so-called standard candles. In astronomy, standard candles are objects whose luminosity is precisely known, and their distance can therefore be directly determined using specific parameters. As Cepheids are very luminous stars, they can also be studied at quite great distances. This method extends to 20 million light years. Before Henrietta Leavitt noticed this relation, astronomers used parallax and triangulation to determine distances up to just a few hundred light years with considerable accuracy. However, the Cepheid method soon became the standard procedure. One of the main tasks of the Hubble Space Telescope from the very beginning was to search for Cepheids in distant galaxies, in order to measure their distances. Another method for determining distance is the Tully-Fisher relation. This is one of the secondary methods and describes an empirical correlation between the rotation curves of spiral galaxies and their overall luminosity. From the shift in the spectra and the resulting rotation speed, it is possible to deduce the luminosity and thus the distance of a galaxy. This can be calculated since light from the spiral arms moving towards us undergoes a slight blue shift, while light from the opposite spiral shows a red shift. This is again the Doppler effect. However, this effect is not measured in visible light, but by measuring the broadness of the 21 cm hydrogen spectral line. A distance value for the galaxy is obtained by comparing the calculated absolute magnitude with the measured apparent brightness. The third method to be mentioned is the Phillips relation, which also is one of the secondary methods. It describes a correlation between the light curves of supernovae, namely those of type 1a, and their absolute brightness or luminosity. Like the Cepheids, this makes them standard candles, but due to their enormous luminosity, distance determination could be extended to very large scales. The Phillips relation also led to the discovery of the accelerated expansion of the universe, for which the Nobel Prize in Physics was awarded in 2011. After so much cosmological theory, let's return to our Milky Way and look at the closer surroundings of our home galaxy. Our galaxy is the second largest in a loose cluster of galaxies, known as the Local Group. This cluster consists of about 70 galaxies. The largest one is the Andromeda Galaxy. About half of the objects in the cluster are companions of the Milky Way, as they are gravitationally bound to our galaxy. The remaining galaxies are, with a few exceptions, all companions of M31, the Andromeda Galaxy, from which we can conclude that our local cluster consists mainly of two dominant systems and their respective satellite galaxies. In addition, the Andromeda Galaxy and the Milky Way influence each other gravitationally. Due to their mutual gravitational binding, they rotate in opposite directions and move towards each other. But more on this later. Such pairs of galaxies are not uncommon in the universe. Many large galaxies are found in couples, as we will see later. The two largest galaxies gravitationally bound to the Milky Way are the Large and Small Magellanic Clouds. Together they orbit the galaxy at almost 180,000 light-years. They were named after Ferdinand Magellan, who discovered them during his circumnavigation in 1519. Both satellite galaxies are in the gravitational field of our Milky Way and are also tied to each other in terms of gravity. The Small Magellanic Cloud, SMC for short, is an irregular galaxy with around 5 billion individual stars. Unlike the Milky Way, it shows no signs of a spiral structure. Instead, it is home to many blue stars and bright reddish gas nebulae. In contrast, the Large Magellanic Cloud, or LMC, has 3 times as many stars and even shows the hint of a spiral arm. The central region appears as a broad bar. The LMC is therefore classified as a barred spiral galaxy. There are mainly red stars here, but also bright gas nebulae and numerous remnants of supernovae. A huge star-forming region, the Tarantula Nebula, also known as 30 Doradus, is located on the LMC's periphery. With a diameter of more than 2,000 light-years, it is almost 70 times larger than the Orion Nebula. The tidal forces acting between the Milky Way and the Magellanic Clouds are so strong that a stream of stars and hydrogen gas has formed, known as the Magellanic Stream. Since its discovery, it has been assumed that the gravitational pull of the Milky Way alone has drawn stars and gas out of the Magellanic Clouds. As other dwarf galaxies have since been discovered orbiting the Milky Way on the same path as the Magellanic Clouds, it is now assumed that several other companion galaxies were also involved in the formation of this stellar stream. In addition to the Magellanic Stream, other stellar streams have also been discovered in the halo of the Milky Way. In any case, these are chains of stars of the same chemical composition and age, orbiting the center of the galaxy on long elliptical orbits. They originate both in globular clusters and in dwarf galaxies that have been captured by our galaxy and are disintegrating due to tidal forces. M33, the Triangulum Galaxy, is the largest of the few galaxies in the Local Group which, as just mentioned, are presumably not gravitationally bound to the Milky Way or the Andromeda Galaxy. It is a textbook example of a galaxy viewed almost perpendicular to the galactic disk. These are also known as face-on galaxies, in contrast to edge-on galaxies, which are viewed exactly in the plane of the disk. In face-on galaxies, the objects embedded in the spiral arms, especially the glowing gas nebulae, star-forming regions and star clusters, are particularly easy to see. The diameter of M33 is about 60,000 light-years, including the outermost edges. It has a mass of about 10 to 40 billion solar masses, which is only about 10% of the mass of our galaxy. The Triangulum Galaxy is around 3 million light-years away. This object is also rich in globular clusters. The largest nebular region even has its own NGC designation, NGC 604, and is a truly gigantic birthplace of stars, as this Hubble image impressively shows. With an extent of almost 1,500 light-years, this is one of the largest star-forming regions known to date. Only the Tarantula Nebula in the LMC is even larger. The Andromeda Galaxy M31 is the brightest galaxy in the night sky. Under good conditions, without disturbing light sources, it is visible to the naked eye as a blurred spot in the sky. In total, it takes up more than twice as much area in the sky as the full moon. However, only the much smaller central region is visible to the naked eye. At around 2.5 million light-years, Andromeda is somewhat closer to us than M33, and with a mass of about 800 billion solar masses, it is the largest member of the local group. The diameter of the visible disk is at least 140,000 light-years. According to other estimates, even more than 200,000 light-years. Studying the Andromeda Galaxy allows us to draw conclusions about our own Milky Way, as both are quite similar in structure. Both have spiral arms that move around the center, which is densely filled with stars and dust. In contrast to M33, however, we do not see M31 exactly from above, but at an angle from the side. The Galaxy Evolution Explorer Telescope, or GALEX for short, was used to better understand the evolution of galaxies. Observation in the ultraviolet wavelength range allows conclusions about the stages of star formation and can localize star-forming regions. The ultraviolet wavelengths mainly indicate the presence of quite young and hot stars, and there are some bright knots, especially in the spiral arms, which indicate extended star-forming regions. A star orbiting the center of the Andromeda Galaxy takes around 300 million years to complete a full orbit. In the infrared spectral range, the cool dust clouds appear bright in the spiral arms, which are dark at visible wavelengths. Like the Milky Way, the Andromeda Galaxy also has numerous companion galaxies. Two of them, M32 and M110 or NGC 205, are elliptical dwarf galaxies, both of which are significantly larger than all the Milky Way's dwarf galaxies together. M31 shows a huge halo in which probably more than 500 globular clusters and large gas accumulations are to be found. This gas seems to originate from supernovae. Research shows that the halo of the Andromeda Galaxy is apparently much larger than previously thought. It extends about 1 million light-years into space, halfway to the Milky Way. Among the many globular clusters of M31, which are all named with the letter G for globular, G1, also known as Mayall 2, is the largest globular cluster known in the local group. It has about twice the mass of Omega Centauri, which is our Milky Way's largest globular cluster. As with Omega Centauri and many other globular clusters in the galaxy, there are reasonable doubts as to whether G1 is really a globular cluster or rather the leftover core of a dwarf galaxy, captured by the gravity of M31. For a long time, it was assumed that the Andromeda Galaxy had a binary core, consisting of two supermassive black holes. It was thought that the second smaller black hole was formed by a collision or merger with another galaxy. Yet, the Hubble Space Telescope proved that the core consists of two rings, the first one composed of older red stars and a second ring of younger blue stars, orbiting a single supermassive black hole. At around 100 million solar masses, it is about 24 times more massive than the black hole at the core of our Milky Way. In addition to the few larger systems, the local group includes dozens of dwarf galaxies. As already mentioned, most of these dwarf galaxies are either satellites of our Milky Way or the Andromeda Galaxy, with a few exceptions. They're all quite small and low in mass, so together they make up less than 10% of the entire mass of the local group. They are characterized by the following features: no visible nuclei, no interstellar matter, no star formation, only a few million stars. Basically, they look like large clusters of stars floating in intergalactic space. However, they can be classified, and scientists distinguish between three subtypes of dwarf galaxies: elliptical, spheroidal, and irregular dwarf galaxies. The elliptical dwarf galaxies can be further subdivided into compact and diffuse ones. The Sculptor dwarf galaxy orbits our Milky Way on roughly the same path as the Magellanic Clouds. This is one of the dwarf galaxies believed to contribute to the Magellanic Stream with stellar streams and gas. But there are probably several galaxies more orbiting the Milky Way on the same path. The Sagittarius Dwarf Irregular Galaxy, or Sagittarius DIG, lies around 3.4 million light-years away. It is believed to be the most remote member of the local group. It is not to be confused with the Sagittarius Elliptical or Spheroidal Dwarf Galaxy, Sagittarius DG. This one is a special case. Like the others just mentioned, it is a companion of the Milky Way and orbits the center of the galaxy on an almost polar orbit. Its distance from the center of the Milky Way is about 50,000 light-years, and its current position as seen from Earth is near the dense central area of the galaxy. The stars of this dwarf galaxy are therefore close to the galactic center in perspective, and thus very difficult to identify in this area with optical telescopes. It was therefore only discovered in 1994. According to measurements, Sagittarius DG will cross the galactic plane within the next 100 million years. It is assumed that the tidal forces of our Milky Way and the interaction with interstellar matter is causing a slow decay process of this dwarf. A stellar stream emanating from Sagittarius DG has formed a swarm of matter, consisting of millions of stars, gas, and dust. It appears that the Milky Way's gravity has a considerable influence on the structure of this dwarf galaxy, and has already swallowed up large parts of it. The Sagittarius Dwarf Elliptical Galaxy even has its own globular cluster, namely M54. This bright globular has been known for over 200 years and is apparently much brighter than the galaxy itself, as it is not obscured by interstellar dust. This means that many of the 150 globular clusters, which are also very similar to the galaxy cores in terms of their stellar population, could be the cores of former merged dwarf galaxies. Astronomers even suspect that most globular clusters are the isolated cores of ancient dwarf galaxies. As already mentioned in the video about the Milky Way, our galaxy's plane shows signs of deformation, which is probably caused by the interaction with the Magellanic Clouds. The inner regions of the disk are flattened, while the outer parts are curved, upwards on one side and downwards on the other. This in turn is a further indication that there must be dark matter in the halo after all. Similar disk curvature is also observed in some other galaxies. Astronomers believe that the gravitational interaction of the Magellanic Clouds with the dark matter in our galaxy causes the interstellar gas at the edge of the Milky Way to resonate. As the Magellanic Clouds orbit the Milky Way and thus pass through the dark matter, the rims of our galaxy move up and down. The distribution of the satellite galaxies around the Milky Way also raises some questions yet to be answered. These are apparently arranged in an almost polar disk, the so-called satellite disk. That's an unexpected finding and a real problem, because the alignment of the galaxies contradicts the assumption that there are large amounts of dark matter in the space between the galaxies. If this were the case, they would have to be widely distributed and disordered around the host galaxy. However, the dwarf galaxies are focused on this huge disk and move in the same direction. Now let's look at the surroundings of the local group. We find several other groups of galaxies here, but we will only take a closer look at the Maffei group and the M81 group. The Maffei group is the closest group of galaxies to the local group at about 10 million light-years. It consists of 24 galaxies. The brightest member is Maffei 1, an elliptical or lenticular galaxy in the constellation of Cassiopeia. Maffei 2 is a medium-sized barred spiral galaxy, likewise in Cassiopeia, not far away from Maffei 1. The entire group is in the center of the galactic plane of the Milky Way, what astronomers call zone of avoidance. This makes them difficult to observe as more than 99% of the galaxy's light is obscured or absorbed by dust clouds and stars in the Milky Way. This is also the case with IC 342, a small spiral galaxy in the constellation Giraffe. Due to the extinction near the galactic equator, it is very difficult to observe. Even more challenging is Dwinga 1, a very faint barred spiral galaxy, also in the constellation of Cassiopeia, nearly in the middle of the galactic plane. As a result, it was only discovered in the mid-1990s. The next galaxy couple, known as the M81 group, which is around 12 million light-years away, is on another level. In addition to the dominant galaxies M81 and M82, this group includes only 7 other galaxies, but it has a lot to offer. They are located at about the same distance as the Maffei group, but far away from the galactic plane towards the constellation of Ursa Major, the Great Bear, where observation is much more favorable. The couple M81 and M82 is a similar pair to the Milky Way and the Andromeda Galaxy, as well as their companion galaxies. However, the distance between them is a lot smaller, about 150,000 light-years, which is less than the distance between the Magellanic Clouds and the Milky Way. Images taken with large telescopes show M81 to be one of the most magnificent galaxies in the sky, with a strikingly symmetrical structure and a dynamic appearance. This beautiful spiral is about the same size as our Milky Way. It also has a very close dwarf galaxy, Holmberg 9, which is visible in the same field of view. With a diameter of 82,000 light-years and an estimated 200 billion stars, M81 is about the same size as our Milky Way. However, the central black hole is much bigger. It has a mass of around 70 million solar masses and is therefore around 15 times more massive than the black hole at the center of our galaxy. The smaller companion galaxy M82, on the other hand, is a very strange object which we see almost exactly from the side, as an edge-on galaxy. Its central region appears to be traversed and divided by dark dust lanes. Images taken with space telescopes at specific wavelengths show an extended nebulous cloud, divided into hazy wisps and filaments along the edges, with dark, irregular, and light-absorbing dust plumes. It appears that these filaments follow strong magnetic fields. They also shine very strongly in the H-alpha spectral range. These gas plumes, which are directed radially from the center, about 10,000 light-years out of the plane of the galaxy, are caused by 2 elongated gas bubbles, aligned almost perpendicular to the disk of M82 and touching in the core. Spectroscopic studies have shown that this matter is moving away from the galaxy's core at about 1,000 kilometers per second. The expanding material has been estimated at around 5 million solar masses. On a cosmic scale, a huge eruption probably occurred recently, less than 2 million years ago, in the central region of M82. This apparently triggered a starburst, in which huge quantities of new stars were formed in the galaxy within a short period of time. The resulting heat and radiation drive masses of gas and dust in the direction of the galaxy poles, from the galaxy's plane into space. The activity of M82 was most likely triggered by gravitational perturbations from the neighboring M81. The interaction with this much more massive galaxy during a close flyby, millions of years ago, changed M82 dramatically. The gravitational pull of M81 altered the orbits of billions of stars and its smaller companion. A direct comparison of visible light and neutral hydrogen gas shows that both galaxies are by no means isolated from the others in the group. Connecting bridges of hydrogen gas are clearly visible, indicating that the galaxies are still interacting with each other. Even the small and irregular companion galaxy NGC 3077, at bottom left, is connected to both larger galaxies. We have already learned that hot hydrogen gas, whose origin is still unknown, is also distributed in the halo of our Milky Way. The processes that take place during the interaction of galaxies also lead to large quantities of gas being torn out of the galaxies, in addition to stars, which are then distributed in the halos. The galaxies move in a common gravitational field, and like all bodies, they react to the tidal forces by accelerating. The extended interstellar gas clouds in the galaxies collide with such great impact that they slow each other down and heat each other up. This process is known as ram pressure. As a result, a large proportion of the interstellar gas is torn out in huge jets. This effect also causes the collapse of the interstellar clouds, triggering the starburst, a temporary strong increase in star formation. All this has already happened in our Milky Way, and we will see more examples of this in the next video, in the topic of interacting galaxies. When looking at galaxies, even a casual observer will notice that they often have a very different appearance. This is referred to as galaxy morphology. However, the question arises as to whether they also have different characteristics, or whether there is a connection between these morphological types. The best-known classification for galaxies is the Hubble sequence, also known as Hubble's tuning fork. It was developed in 1936 by Edwin Hubble, who regarded this model as a possible evolutionary sequence for galaxies. Hubble was convinced that all galaxies were initially ellipticals, and that they transformed into spiral galaxies during their development and with increasing age. We will see later that Hubble was wrong on this point, and probably it's the other way around. The extended Hubble sequence includes 3 main groups and 2 special types of galaxies. On the left side, we have elliptical galaxies, where the eccentricity increases from subclass E0 to E7. These different manifestations of elliptical galaxies are largely due to perspective effects. E0 elliptical galaxies are face-on, while the more we look at their edges, the more elongated they appear. Consequently, E7 ellipticals are edge-on galaxies. Therefore, the numerical classification of elliptical galaxies is not necessarily relevant from an astrophysical point of view. The second third of the Hubble sequence is taken up by the spiral galaxies. In them, the size of the nucleus, the density of the spiral arms, and the proportion of dust and gas within the galaxy decrease from subclasses A to C. The same applies to barred spirals, with which the tuning fork is completed. The special cases mentioned are the lenticular and irregular galaxies. These have their own spots in the diagram, as they did not fit exactly into the scheme when it was created. However, the main problem with the Hubble sequence is that Edwin Hubble only managed to observe a few hundred galaxies, all of them being quite close, due to the insufficient technology available at the time. Furthermore, the Hubble sequence is limited to the appearance of galaxies in optical spectral range. In other wavelengths, galaxies usually look quite different. As a result of these issues, today, the Hubble sequence is only used to a very limited extent, despite some efforts to enhance the sequence, for example, by French astronomer Gerard de Vaucouleurs in 1959. In his classification system, galaxies are categorized according to the properties of the spiral arms and the presence of rings and barred nuclei. In 2008, the Spitzer Space Telescope examined 75 of our nearest galaxies in infrared light, as part of the Spitzer Infrared Nearby Galaxy Survey, or SINGS for short. In the infrared images, old stars appear blue, while dust and gas are shown in red. Elliptical galaxies tend to appear bluish in this image, as these galaxies are dominated by old and red stars. This strongly suggests that the gas required for star formation is almost depleted. Spiral galaxies are shown here in green and reddish colors because star formation takes place mainly in the spiral arms, while almost no stars are formed in the central parts, which are dominated by old stellar populations. The observations in infrared support theoretical considerations, as well as simulations and earlier observations that elliptical galaxies have developed from spiral galaxies, and not the other way around, as Edwin Hubble assumed. Let's take a closer look at elliptical galaxies. Their ellipticity is mainly due to perspective, but not exclusively. Less luminous elliptical galaxies can be flattened due to their rotation, while the brighter and more massive ones tend to be oval or spherical. It is interesting to note that the most massive elliptical galaxies have been found to partially spin around their major axis. We will come back to this later. Elliptical galaxies do not show any special structures. In contrast to the Milky Way and other spiral galaxies, they are not disc-shaped, but have a spatial structure, meaning that they are either spheroidal or elliptical. In other words, they are shaped like an egg or a football. They are bright in their center, with brightness decreasing rapidly towards the edges. The lines of equal brightness, the isophotes, can be described quite precisely by concentric ellipses. It was previously assumed that there was practically no gas and dust in these galaxies. However, observations in the X-ray range have indeed detected hot gas. In addition, up to 50% of elliptical galaxies show a higher proportion of dust. Most of them consist mainly of older stars of population 2. They are often found in rich galaxy clusters. The largest and most massive galaxies are elliptical. They were probably formed by the merging of several small to medium-sized galaxies. One of the closest giants is M87, with a mass of around 3 trillion solar masses. It is surrounded by 12,000 globular clusters inside a gigantic halo. Like most giant elliptical galaxies, M87 is located in the center of a large galaxy cluster. Giant galaxies like this one are probably almost always the result of galaxy collisions, when various galaxies of similar size and mass are merged. In the last video, we mentioned the core of M87, which is home to a colossal and very active supermassive black hole with more than 6 billion solar masses. This makes M87 a so-called active galaxy. We will find out more about these objects in the next video. Studying the motion of stars in the largest and most massive elliptical galaxies, using the Multi-Unit Spectroscopic Explorer at the European Southern Observatory's Very Large Telescope, scientists have found a surprise. The resulting maps of the measured average stellar velocities show two different rotational variations. Blue means that the stars in this part of the galaxy are moving towards us. Red means that they are moving away from us. While one half of the investigated very massive elliptical galaxy spins around its minor axis as expected, the other half rotates around its major axis. Numerical simulations show that the rotation along the major axis may be caused by the merging of two galaxies of similar size and mass, if this occurs on specific orbits. Likewise, the peculiar rings or shells, seen in some elliptical galaxies, are most likely the result of mergers. These shells consist of stars arranged in thin envelopes. But more on that in the next video, when we get to the topic of galaxy merging and galaxy cannibalism. Lenticular galaxies make up a special case in the Hubble diagram, which is why they have been given their own category, S0. They look like a mixture of spiral and elliptical galaxies. Their nuclei resemble those of spiral galaxies. They show no spiral arms in their disk. Instead, it is evenly bright, like elliptical galaxies. However, S0 galaxies appear to have more in common with spirals than with ellipticals. They are disc-shaped and have a distinct central bulge. They also have a significantly higher dust content. Most S0 galaxies can be recognized as such by studying the outer regions. Beyond that, it is also possible to distinguish them from elliptical galaxies via their spectra. As we have seen with the Milky Way, spiral galaxies have a characteristic almost spherical core and spiral arms extending from it, forming a flat disk. The spiral arms are further divided into three subclasses, SA, SB, and SC, depending on how tightly they are wrapped or curled around the nucleus. The SA type has a very pronounced core and tightly wound spiral arms, while the SC type shows a relatively weak core and loosely wound arms. The central bulge resembles a small elliptical galaxy. Star formation does not take place here. Instead, gas and dust inside the disk enable star formation only in the spiral arms. These are often shown bluish in many images, while the bulge usually shimmers in reddish light. As you remember, the different stellar populations are reflected here. Grand design spirals show two clearly defined and symmetrical arms. They make up 10 to 20% of all known spiral galaxies. Flocculent spirals have a torn or fragmented structure. It is not possible to point out complete spiral arms. In some cases, only the initial parts of the arms are evident. Around 20 to 30% of spiral galaxies are flocculent spirals. Together with barred spirals and lenticular galaxies, they are also referred to as disk galaxies. Barred spirals feature a long bar, starting from the center and continued by the spiral arms. With increasing development of the nucleus and widening of the spiral arms, these galaxies are divided into the subclasses SBA, SBB, and SBC. SBA galaxies have a large bar-shaped core. The spiral arms are almost ring-shaped and closed. SBB galaxies have more pronounced arms and a weaker core. Finally, SBC barred spirals are S-shaped with only slightly curved arms. Instead of a nucleus, they only show a central thickening. Barred spirals are the most common type of galaxy, with around 70% of all spirals in our intergalactic neighborhood having a barred structure, as we have seen, including the Milky Way. It was previously thought that the bars form when the almost circular orbits of the stars circling the center of an ordinary spiral galaxy become unstable and take on an elliptical shape. According to this theory, the bar structure would be related to the mysterious density waves that propagate radially from the center of the galaxy, affecting the orbits of the inner stars. We already heard about density waves in our last video. It seems that barred spirals are just a temporary stage in the evolution of galaxies, and they continue to develop into regular spiral galaxies over time. A spiral galaxy goes through all stages of development from spiral to barred spiral over a period of several billion years, unless it is affected by interactions with other galaxies. Recent observations, especially at non-optical wavelengths, have also shown that the barred central regions usually show active star formation. Infrared imaging of this face-on galaxy reveals the gas from which stars are formed is apparently flowing from the spiral arms to the center of the galaxy. The black hole located in this galaxy's core, which has about 100 million solar masses, is surrounded by a ring of star-forming matter, 5,000 light-years wide. Perhaps these gas streams also ensure that the supermassive black hole is fed with incoming matter. To conclude, the second special case in the Hubble tuning fork concerns irregular galaxies. These have neither spiral arms nor an elliptical shape. On average, they are less luminous than elliptical and spiral galaxies. Most dwarf galaxies are part of this group. Many systems interact with neighboring galaxies or show signs of activity. In other words, the irregularity of some of these galaxies is the result of a morphological alteration caused by gravitational interaction. In the next part, we will venture further out into the universe, where billions more galaxies are waiting for us. Thank you for your attention. Please leave a like to this video and subscribe to my channel. Thanks for your support, and see you soon.